Our next speaker is Dr. Wolfgang Hoffmann from the Center for Expert Systems in Dortmund, Germany. In his presentation, Dr. Hoffmann will discuss the application of device-specific neural networks for system fault diagnosis.
Ladies and gentlemen, I'm glad to have the opportunity to present to you an ANN applications to electrical power systems that, to my opinion, is most promising and may help to guarantee the security and the reliability of electrical power supply in the future. The co-authors of this presentation are Professor Hanshin, who holds the chair of electrical power engineering at the University of Dortmund, and Dietmar Kuhlmann, who is working as a researcher at his institute. After my brief introduction, I would like to explain to you the task of fault diagnosis in electrical power systems, with special respect to the characteristics that are typical for the different types of electrical power systems like transmission systems and distribution systems. After that, I would like to explain to you why the most straightforward application of artificial neural networks to that task will not be successful, and the concept of device-specific artificial neural networks will be presented after that. An example helps me to make clear how the device-specific artificial neural network-based approach to a system fault diagnosis works. And I will conclude my presentation with a description of the state-of-the-art of the project and with an outlook what we are going to do next. The task of fault diagnosis in electrical power systems can be described by using this slide. The faults in electrical power systems can cause severe damage to components of the electrical power systems, and they can cause danger to the personnel and to other people who are working next to the faulty element. Therefore, lots of protection devices are installed in the electrical power systems. For example, lines are protected by protection relays, which are installed at the end and at the beginning of the lines. And it's a task of this protection system, of this protection relays, to detect electrical faults and to switch them off selectively and as fast as possible. So the protection relays installed at a certain line, for example, do generate messages and alarms, and these may be sent to a central control center where the operator of the electrical power system has to draw the conclusion where the location of the fault can be. That is most simple if at the beginning and at the end of the line the protection relays detect a fault on the line. They do generate messages, and the operator has just to draw the conclusion that the fault is in between both protection relays. But as the task of switching off faults, of disconnecting faulty elements from the electrical power system is such an important one, there are redundancies. There are lots of protection devices installed in the electrical power system, and they partly work as backup protection devices, so that in the case of a certain fault, not only the protection relays assigned to that electrical element, but lots of other protection devices distributed in the electrical power system can detect the fault, can generate messages, and these messages can be transferred to the control center of an electrical power system. In the control center of that electrical power system, it's a task of the operator to analyze the alarms received, and this task might be difficult because of different reasons. In the case that the telecommunication system is fully installed, this means that all the messages and alarms generated by the protection relays are transmitted to the control center. In that case, an information overflow may cause problems to the operator to analyze the alarms. The size of the electrical power system has to be taken into account, and the operator has to put together the information, the alarms he received with his knowledge on the actual system topology, and has to draw conclusions from that. This might be difficult. In distribution systems, often because of economic reasons, the telecommunication system is not fully installed. This means that not all substations are linked to the to the telecommunication system, and therefore not all alarms and messages generated in the electrical power system are transmitted to the central control center. Therefore, the operator has to draw conclusions from incomplete sets of alarms, and maybe even the protection devices installed in the electrical power systems are not adjusted correctly so that they generate alarms, faulty alarms, that they generate alarms even in the case that they shouldn't do that. And so the operator has to deal with wrong alarms as well. There have been several approaches to help the operator to find his decision, to analyze the alarms received in the control center. The first one was to assign certain priorities to the alarms. This may lead to wrong decisions in the case that the set of alarms is incomplete, when there are missing alarms of high priority. Maybe the alarms of less priority are suppressed and the operator has not enough information to draw his conclusion. Another approach is the application of expert systems. Expert systems allow to implement rules in the knowledge base of the expert system. These rules can describe the interconnection between a certain set of alarms and a certain conclusion. This means a certain location of the fault in the electrical power system. The drawback or the bottleneck of that approach is that the expert system can draw conclusions only from rules that have been implemented. So in the case of incomplete alarm sets, often the expert system failed to find the location of the fault in the electrical power system. And that was the reason for trying to apply an artificial neural network approach to the task of system fault diagnosis. From other applications of artificial neural networks, we know that the artificial neural networks are robust with respect to missing input data, and that's exactly what we want to use to implement a more powerful system for fault diagnosis in electrical power systems. The application of artificial neural networks to the task of fault diagnosis can be most straightforward. For example, alarms generated in the electrical power systems, generated by the protection devices, they can be used as input data to the artificial neural network. The input layer so accepts information from the circuit breaker or from the protection relays and draws conclusion in the way that in the output layer of the artificial neural network, the diagnosis is shown to the user of such a system. So the artificial neural network has to learn, as Bob Marks explained, for example, by applying a backpropagation algorithm, has to learn the nonlinear function that links a certain set of alarms and messages to a certain diagnosis. You can imagine that this nonlinear function describing the input and the output relation of the task of fault diagnosis depends very much on the actual topology of the electrical power system. Doing switching operations in the electrical power system will cause that the same fault will lead to another set of alarms, and regarding the application of just one artificial neural network to the task of power system fault diagnosis is most inflexible, because the artificial neural network would have to be retrained after each change in the topology of the electrical power system. The training of the artificial neural network that has to learn about the relations between the set of alarms and the diagnosis is very complicated if you apply this straightforward approach, and that was a reason for us to break down the electrical power system to the level of devices, to a level of components of the electrical power system that does not change and that do not change their topology. And the artificial neural network does the diagnosis for those subparts of the whole electrical power system. This means that an artificial neural network, we call it device-specific artificial neural network, or abbreviated DSANN. The device-specific artificial neural network for fault diagnosis gets as input data the alarms assigned to a specific device and generates the diagnosis related to this very device. You can imagine that the fault diagnosis can be done by such a device-specific artificial neural network only in the case that the input data, so the alarms assigned to a certain device, are available in the control center and are completely available in the control center. Unfortunately, we have to deal with electrical power systems and with real situations. This means with incomplete data. And therefore, we implemented a device-specific artificial neural network approach in order to be able to deal with incomplete bursts of alarms. We do not anymore rely on the alarms assigned to a certain device, but we do use intermediate diagnosis provided by contiguous device-specific artificial neural networks as well as input data. And the diagnosis generated by the DSANN are transferred to the contiguous DSANN so that they can apply these intermediate diagnoses as input data in the next step of the iterative process. The information flow is described by the electrical power system. So we can see that, for example, the device-specific artificial neural network applied for the busbar B1 gets as input data the alarms assigned to busbar B1, as well as the intermediate diagnosis generated by the device-specific artificial neural networks assigned to line 1, as well as the results of the device-specific artificial neural networks applied to line L2 and line L3. So intermediate results are passed to contiguous device-specific artificial neural networks. And in an iterative process, the intermediate results are passed backwards as well. I already said that the fault diagnosis in electrical power systems applying the device-specific artificial neural networks is done in an iterative process. And how this works can be seen on the next transparency. The electrical power system generates, the protection system in the electrical power system generates messages and alarms. In the case of a fault in the electrical power system, these alarms are stored in a vector of alarms. A certain set of alarms of this total vector is applied as an input vector to a device-specific artificial neural network doing the diagnosis for a certain device. This DSANN, this diagnosis is done by one of the predefined device-specific artificial neural networks that have to be applied to devices like lines, to devices like bus bars, to devices like transformers. The diagnoses generated by the device-specific artificial neural network are stored. These are intermediate diagnoses. They are stored in the vector D in order to be applied as input data as well in the second iteration. The way how the information has to be passed to a certain device-specific artificial neural network, in other words, which set of the overall set of alarms has to be used as an input information for the diagnosis of a certain line, is described by the matrix Mi. This matrix, as well as the matrix Ni, are generated in an offline process, and they are generated automatically from the actual electrical power system topology. This offline process takes 5 seconds on an alpha workstation, for example, so it's a reasonable time. It can be done offline, and the matrices Mi and Ni afterwards describe how the alarms and how the intermediate diagnosis have to be used as input data for a certain device-specific artificial neural network doing the fault diagnosis, for example, for a certain line. It's worth mentioning that there are device-specific artificial neural networks for fault diagnosis, for example, for lines, that there is only one artificial neural network doing that fault diagnosis. We do not have to to train artificial neural networks for each line, but the same trained artificial neural network can do the fault diagnosis for all lines subsequently, just by making sure that the input vector is related to a certain line. Makes the device-specific artificial neural network generates the diagnosis related to that very line. An example will show you how the diagnosis process works and how, starting from a certain fault, we assume a fault on line 2, how the alarms generated and transmitted to the control center are analyzed by the artificial neural network, and how the intermediate diagnosis focus on the final diagnosis. There are power injections at bus bars 4 and 6. And in the case of a fault on line L2, the related protection device at bus bar 3, feeder A, detects the overcurrent, but it fails to submit the switching command to the related circuit breaker, so that the backup protection devices have to switch off the fault on line L2. These backup protection devices are located at bus bar 4, feeder A, where we can see that the overcurrent detection alarm was generated, the circuit breaker tripping command was generated, and the message that the circuit breaker really tripped are available in the central control center as well. The same information we do have from bus bar 5, feeder A, where the circuit breaker was tripped as well. Some other protection devices located at bus bar 6 and bus bar 7 did recognize the overcurrent as well, but they did not trip. At least we do not know whether they tripped the circuit breaker or not. It's important to know that bus 2, substation 2, is not linked to the telecommunication system, so that we do not know anything from substation 2. And this is a situation. These alarms are used as input information for the device-specific artificial neural networks in the fault diagnosis process I would like to explain to you. In the first iteration, the first part of the first iteration, the diagnoses are done for the device's lines. Subsequently, the device-specific artificial neural network trained for doing the fault diagnosis for lines is provided with the related input data for each line and does a diagnosis for all lines. The next slide shows the intermediate results, and we can see that, for example, line 5 is called to be a probable location of the fault because of the fact that at the beginning of line 5, an overcurrent has been detected, so it's possible that the fault is on the line L5. The same with the lines 3 and line 4. Even more, it's probable that the fault is located on the line L3 or line L4 because of the fact that the circuit breakers have been tripped at these lines. The intermediate diagnosis related to line L8 is the same as related to line L2. All the lines marked on this slide are called probable location of the fault in the first half iteration of the fault diagnosis process. In the second half of the first iteration of the fault diagnosis process, the DSANN related doing the fault diagnosis for bus bars are applied, and subsequently the DSANN doing the fault diagnosis for bus bars is provided with the related alarms related to the bus bars of the electrical power system. And we can see that the bus bar 2 is called to be a probable location of the fault because of the fact that there are intermediate diagnoses provided from the contiguous lines, from lines L2 and line L3. These intermediate diagnoses, for example, the intermediate diagnosis of L2, line 2, it says that the fault can be on the line or further on left of the line. The same as intermediate diagnosis generated by the DSANN when it was applied to line L8. The fault could be on line L8 or it can be further on left of the line. That's the reason there are two indications that the fault might be on busbar 2, and busbar 2 is part of the set of probable location of the faults. We can see that busbars 5 and 3 are not called a probable location of the fault. This is because of the fact that, on the one hand, the intermediate diagnosis generated for line L5 indicates that the fault may be on the line or further on the left side. So this intermediate diagnosis would give evidence for the fact that the busbar has to be called a probable location of the fault. But on the other hand, the intermediate diagnosis for line 4 says that the fault can be on the line or left of it. This means the intermediate diagnosis is contradictory to the fact busbar 5 is a probable location of the fault. The same arguments are against busbar 3 as part of the probable location of the faults. In the first part of the second iteration, the device-specific artificial neural networks that does a diagnosing process for lines is applied, and we can see that, for example, line L5 is not called part of the probable location of the fault anymore because of the fact that the line and the intermediate diagnosis generated for busbar 5 is that the fault is on line L4 or even further to the left side. This intermediate diagnosis is provided to the DSANN doing the diagnosis for line L5, and the result is that the line isn't called anymore part of the probable location of the faults. In the same way, the first intermediate diagnosis has been reversed, so the lines L3 and lines L4 are not called a part of the probable location of the fault anymore. The intermediate diagnosis for lines L2 and line 8 is still the same. The location could be on these lines. The intermediate diagnosis of the busbar is the same because we didn't apply the DSN a second time for the busbars. But the fact that the busbar, the intermediate diagnosis generated for the busbar tells the DSANN applied for line L1 that the fault can be on the busbar or even further to the left side, causes the diagnosis generated for line L1 that the fault can be on this line as well. So the final result after 3 iterations, this means after 3 iterations the intermediate results do not change anymore, and that's the criterion when we do stop the iterative process. The final result after 3 iterations is that only the line L2, the real location of the fault, and the connected busbar are called to be a probable location of the fault. All other intermediate diagnoses regarding lines 3, 4, 5, 6, and 8 could be retracted, and this is the optimal interpretation of the information available in the control center. You remember that busbar 2 or substation 2 are not connected to the telecontrol system, so that there is no information available, and we do not know that busbar 2 did disconnect the fault on line L2. I think the result is quite impressive, and I would like to explain to you a little bit how we came to work on that topic and how the actual state of the project is, in which we had the chance to realize this DSANN-based system for fault diagnosis and the actual state of the project. The DSANN-based system for fault diagnosis has been realized as a part of a 3-year joint project, partly funded by the German government. The project has been carried out together with 3 industrial partners, vendors of EMS systems. The main contractor was AEG, and we had the chance to integrate different ANN-based solutions. That was the major aim of the project, the integration of an implementation and integration of different ANN-based online solutions into an EMS system. The tasks to the rest are the topology processing. This means deciding on whether certain lines and busbars are still under power or not after switching operations. The load forecasting is a well-known application of artificial neural networks. the security assessment. We addressed this static security assessment in this case, and it was our task to realize a fault diagnosis system based on the DSANN concept. All the systems have been integrated into the EMS software and have been tested with data a customer of AEG provided, so that we had a chance to do the test under real conditions. A field test unfortunately could not be done during the project, during this 3 years project, but we are looking forward to do it in the near future. The results of the test showed that the device-specific artificial neural network approach to fault diagnosis does an effective, fast, and reliable fault diagnosis. It shows that the computational time demand of this approach is really impressively low compared to the expert system approach, which we realized at the CEDAW as well. It's about 30 times faster than the expert system approach, and this time demand increases linearly with the number of devices included in the electrical power system. This is important to emphasize that the number of iterations depends only on the quality of the information available and not on the size of the electrical power system. The number of iteration depends, and you can imagine that at the end and at the beginning of a certain line, the circuit breakers are tripped by the protection devices, and these information are available in the central control center. You can imagine that the fault diagnosis process comes to an end very rapidly. Only if the information is incomplete and intermediate diagnoses have to be transferred from one device-specific artificial neural networks to others, this takes some iterations until the final result can be achieved. Typically, the device-specific artificial neural network approach to fault diagnosis comes to a diagnosis after 0.5 second, up to 1 second, maybe on a DEC alpha machine on which we run the EMS system. This very short time demand of the device-specific artificial neural network approach to fault diagnosis allows for an online fault diagnosis. This means that alarms and messages can be included in the fault diagnosis process as soon as they are available in the control center. And the result of the intermediate diagnosis and the result of the diagnosis can be displayed on the screen to the operator as soon as information are available. In an early stage of this project, we did a comparison between an expert system approach to fault diagnosis we implemented in the past and the new DSANN-based approach to fault diagnosis. And we found that because of the fact that expert systems have been subject to research and development for a much longer time, the availability of tools is much better for the expert system approach to fault diagnosis than compared to the DSANN-based fault diagnosis. The explanation of results can be done by expert systems. Of course, that is a drawback of the DSANN-based solution, where we do not know why the artificial neural network comes to a certain result. The robustness, of course, is an advantage of the ANN-based approach. Typically, for the artificial neural networks, they are able to deal with incomplete input information. And of course, the speed is a major advantage of the DSANN-based approach to fault diagnosis. At that point of time, we decided to sell an alarm processing system to an industrial project partner and to realize that by applying the expert system technology. From the today's point of view, we of course would prefer the DSANN-based approach to realize the same task, because the risk of failure does not exist anymore. We are pretty sure that the new DSANN-based approach to fault diagnosis is as powerful and much faster than the expert system approach is. So let me conclude that the DSANN-based approach to fault diagnosis I presented to you consists of two tasks. The first task is in an offline process describing the way how intermediate information have to be passed between the DSANN, so how the DSANN have to be linked together according to the actual topology of the electrical power system. And of course, in an offline tasks, the different DSANN have to be trained in order so that they can do the fault diagnosing for devices like lines, bus bars, transformers, and other components of the electrical power system. And in the online process, the alarms generated in the field are transmitted to the DSANN-based fault diagnosis system, and the result can be displayed to the operator by using the same man-machine interface he is familiar with. The DSANN-based solution of the task of system fault diagnosis is flexible. It's not network specific, so we do not train the artificial neural networks with any respect to a certain power system. They can be trained independently from that. They are trained in a case that they can deal with different concepts of protection devices. They can deal with the overcurrent protection with a distance relay as well as with differential relays. And there is no need for retraining the DSANN whenever the topology of the electrical power system changes. This is one of the major advantages of this approach. You remember that the most straightforward application of artificial neural networks to the task of fault diagnosis, this means just applying the burst of alarms as an input vector and trying to train the artificial neural network in a way that the output vector gives the diagnosis, must fail in the case of changing network topologies. Our approach to apply DSANN to the task of fault diagnosis avoids that problem. We do not need any a priori information on the installed protection relays because the DSANN are trained in a way that they can deal with a broad variety of different protection relay systems. And we found that the iterative procedure applied in the DSANN-based fault diagnosis system allows to limit the probable location of the fault to that area of the electrical power system that is described in the burst of information and the burst of alarms available in the central control center. I already said that the actual state of the project is that we are looking forward to do a field test in the next future, and I would be happy to have a chance to report on the results in the future. Thank you very much for listening.
Our final speaker is Professor Kwang Lee from Pennsylvania State University. He will talk about the potential use of neural network in control. More specifically, he will discuss the application of recurrent neural network for generator excitation control in order to enhance the system stability.
This portion of the lecture is going to be control over power systems aspect for application of neural networks in electric power systems. And I'll be going over this sequence. First, we'll talk about introduction, and then some of the background of neural networks applications to control aspect. And then we'll talk about neural network architectures for modeling and control. And then we will go on to supervised neural network structures. And then in particular, we will focus on diagonal recurrent neural network-based control system as an example. And then we'll talk about some of the convergence and the stability properties. And then finally, we will talk about application to nuclear reactor control problems. And then we will conclude with some remarks. First, in terms of history behind control applications, in 1987, we have Widrow and Smith paper on ADALIN, which is adaptive linear element control over an inverted pendulum. And then for several years in 1970s, Elbus developed a new architecture called Cerebella Model Articulation Controller, which is a CMAC, in order to control robotic manipulators. And then later, he modified ADALIN to make modeling by including perceptrons architecture combined with Adeline for binary coding of the input space. Here is some example of applications in controls and identification area. First, Chow and Thomas applied it to machine modeling problems. And then Santos and Tan worked on capacitor control in distribution system. And then Virasuria and El Shakawi in 1991 worked on identification and control of DC motor using neural networks. And then later, Wu and others worked on neural network regulator for a turbo generator problem. Also, Cho and others worked on neural fuzzy controller by combining neural network and fuzzy logics for induction machine. And then Xu and Chen and Seto and Zhang and numerous other people worked on power system stabilizers and good control applications. In particular, Hiyama later applied the neural network controller to control a photovoltaic system. And then also Buffet and Widrow worked on low frequency control problems. Also, you can see that Neely and others worked on joint VAR controller. And then later, it was also applied to coordinated control problem of excitant generator. Finally, Park, Choi, and Lee worked on decentralized control for power system stabilizers. And then also Cooley and Edward worked on online control of a nuclear reactor, which we will see as an example later. Okay, now I'd like to talk about architectures for modeling and control. First, we begin with the representation of a plant in terms of models. There are three types of models. Continuous time representation, also discrete time representation, and normal representations, which means nonlinear autoregressive moving average representations. And regardless of the representations, neural network is going to model these behaviors according to these representations, and then based upon the model, we will develop controls. Now, let's take a look at learning model architectures, how neural network is utilized to model plant dynamics for control purpose. There are four types of architectures. First, we have A, which is forward plant modeling architectures. And then secondly, we have B, inverse plant modeling architectures. Forward modeling architecture models unknown plant in terms of system identifications by using input and output measurement. On the other hand, inverse plant modeling is trying to map the inverse of the dynamics or unknown plant by using the plant input and output, and then come up with the plant input, which is compared with the applied input of, in the system. Also, there are two other types of architectures, which is C, specialized inverse plant modeling. And this one makes use of two models. One is the forward plant model in part A, and then inverse plant model in part B. By combining the two, we can model the unknown plant better. Finally, we have what we call operator modeling. In other words, here is an expert controlling unknown plant manually, and then this operator model mimics this expert activities, and then later this expert can be replaced by this operator model to control the same thing. Now let's take a look at the first one, which is learning modeling architectures. This one, we are modeling unknown plant in terms of a forward modeling approach. So here is applied input to the model, and then here is output of the plant. By comparing the plant output and the output of the unknown plant, the error is utilized to learn and then tuning the plant model. So here we are minimizing the error between plant output and then plant reference output, and then that error is minimized. So this is used for prediction purpose of the plant performance, and then also for making fault diagnosis problems. The second architecture is inverse modeling. Here is input to the plant applied, and then output of the plant is also applied, and then it produces output signal which is compared with the actual output signal, input signal applied, and then error is used to learn the inverse model. This one, the overall controlled plant architectures has a unity transfer function. In other words, by having inverse model in the forward loop for control purpose, the total gain is equal to 1. This one, you have a modeling error perturbs the transfer function away from unity. And then another property is if we combine it with the feedback control, it can give us good performance. And so the type of modeling architecture is specialized inverse plant modeling. Here we have a forward model and then inverse model combined, and unity feedback transfer function. Unity transfer function is achievable by using the inverse plant model. And the forward plant model is first constructed, and then the error is back propagated to the inverse model, as you can see, to tune the second the model. And this is goal-driven plant error. The goal-driven plant error causes the inverse model to move away, move into previously unexplored regions of input space. And however, this is not as robust as other types because there is no feedback mechanism. The final type is operator modeling. Here is an expert operator, such as you or a human being, controlling unknown plant. And then this operator model is learning what expert is doing by comparing input and output of the expert controller, and then the error is utilized to tune the operator model. This one is not very accurate because there are a number of different actions that operator can do to do the same function. In other words, there is no unique mapping between expert and the operator model. And also, there are a lot of noises. Being human, you have a lot of different activities which will still perform the same function. Okay, now we are moving into a supervised control architecture. This architecture, we have a fixed stabilizing controllers will control the plant. And then also we have a predictable learning control scheme that is available. And then we have a model reference adaptive control is available. Finally, internal model control will be explained. First, we have a fixed stabilizing controllers. Here we have a stabilizing feedback controller controlling the plant as usual by using feedback signal. And then the performance of this controller is monitored by learning inverse model, and then the performance is improved. Okay, and this is a direct learning control scheme, and then also the closed loop system is stable in every operating region. Finally, a learning controller builds up a nonlinear model of the desired control surface. Okay, another type of a supervised control architecture is predictable learning control scheme. The power plant, for example, such as the boiler, you have a lot of lead time. So there is enough room to make some predictions before you actually apply control. So here we formulate the control strategy by assessing the effect of its action into the future and select the optimal control action. In other words, this is the usual controller, and then this is assessment or optimization function. In other words, by using plant model in a predictive mode, and then by comparing the output of the plant response, and then you make some kind of assessment whether that action is appropriate. Once you decide it is okay, then that controller or decision is made available to control the actual plant. So this is a learning control, and it has excellent closed-loop control for good plant model with the proper performance function and the search strategy. Another type is, which is popular one, is a model reference adaptive control scheme. Here we have a reference model, and the reference model is producing a idealistic response based upon a set point or input signal which is applied to the controller. And then the response of the response model and the actual plant response is compared, and then the error is used to tune the controller. And here, performance depends upon the choice of a suitable reference model and the learning mechanism. You have to have a reasonable model which will not stress the controller too much. And then also, how do you make the learning mechanism efficient so that you can use it for online control purpose. And that is very important for this type of controller. Another type of supervised control architectures is internal model control. We model the process directly. In other words, here is plant model, models plant directory, and then the error is compared, and then that is used as a feedback signal to make a further adjustment to control. Error between the model and the plant output is used as a feedback signal, just like the feedback control loop. And the internal model control is designed to be an inverse plant model. Okay. In other words, this is designed offline by using an inverse modeling scheme that I have described. And stability results are available with assumptions on the open loop stability, exact modeling, and or inverse modeling. There is another type of control, is reinforcement learning systems. Okay. This one is making use of two blocks. One is adaptive critic element. Another one is associative critic search learning. Associative search learning produces the optimal control signal. So any types of controller can be in this block. However, we have additional block which is called adaptive critic element, which monitors the performance of the controller. In other words, here we have a signal applied, and then here we have output response monitored, and then performance of the controller is evaluated, and then if it is not satisfactory, then additional reinforcement signal is applied to the controller. Another controller is intelligent gain scheduling approach. This is a conventional PID controller, which is normally fixed for a particular operating point to control the plant. However, the gain of a controller can be adjusted by using external loop, which is called associative memory mapping. In other words, suppose we want to have some performance to be achieved in terms of rise time or overshoot of the plant response. And then we are making comparison between the actual response of the plant and the desired one. And then the error is used to tune the gain of the controller. Now, going into more specifics in terms of supervised neural network structures, there are basically three types of neural network structures. First, most popular one is multi-layer feed-forward networks. Here, input signal is propagated forward through several processing layers, and feed-forward network is a static mapping, however. In other words, you have to have tapped delays in order to represent the dynamic mapping. And often, we need to have dynamic compensators or controllers for control purpose. For that purpose, we have to have a number of tapped delays, which makes the network larger and complicated. Another type of a network is radial basis function network. This mimics the biological paradigm in favor of topology and the simpler and the more amenable for training. This one has a single layer of a hidden node with the radially symmetric basis activation function. And above all, the important property of RBN is locally responsive. In other words, we don't have to change all neurons when you train. Only the smaller subset of the network can be trained depending upon the input signal. And then another important class of neural network is recurrent neural networks. This RNA is similar to a feed-forward neural network. However, in addition to that, it has some feedbacks. Therefore, it can be used to model nonlinear dynamic networks, and has attractor dynamics and store information for later use, since it has feedbacks. It can also deal with the time-varying input-output signals, and it is certainly a dynamic mapping. You don't really need external feedback like the feed-forward neural network case. So there are no or fewer external feedbacks. However, since you have feedbacks in many of the neurons, training might be difficult. So as a compromise, now we have an alternative architecture, which is called diagonal recurrent neural networks. This one, you have feedbacks, but only in this neuron, in the hidden layer, and you have output applied to input in terms of feedback. So you only use self-recurrency rather than crosstalks. You don't connect one neuron to another neuron through feedback passage. So this way, this is a minimal variation, and you have fewer weight to train. So real-time application is possible. Now, using this diagonal recurrent neural network, we can design a control system, and there are two types of neural networks being utilized. Okay, one is neural identifier to model the plant, and also provide the sensitivity to the neural controller. And neural controller follows the plant model. In order to make it applicable for online control, dynamic backpropagation can be utilized, and then also the convergence and the stability should be guaranteed. So this diagram shows the architecture. This is the plant that you want to control, and this is the reference model which you want to follow. And the difference between actual response of the plant and the reference model is used to train the neural controller using dynamic backpropagation algorithm. Similarly, neural identifier is used to model the plant, and here the input of the plant, then output of the plant is compared with the output of the identifier, and then error is used to train the neural identifier. In addition to that, the sensitivity function is available within identifier, and that is passed to neural controller for training purpose. Now let's take a look at application of this diagonal neural network-based controller, and we are applying this to nuclear reactor control problem. Nuclear reactor is described by these following equations, and the first equation is equation corresponding to neutrons, and then second equation is for precursor density, and then it can be represented in terms of the normalized equations, as you can see. In addition to neutron and the precursor density, we have a temperature dynamics. Temperature in terms of fuel temperature, T sub F, and then also temperature leaving the reactor, T sub L. Finally, we have control rod dynamics in terms of rod speed applied, then the rod is going to move. And the density of the reactor is d sub rho, and that is applied to the reactor model non-linearly. So the whole equation is non-linear plant, and also depending upon operating point, it exhibits quite different properties. So altogether, we have second order for reactor, and then second order for thermohydraulics, and then additional order for control rod. So you have a fifth order model to play with. We have divided the operation region into 9 regions in terms of power output, 10%, 50%, and then 100% power output. And also the control rod was changed, signifying that the aging of the fuel. So this is kind of a nominal control rod, and this is the smallest. This is the highest control rod. So here, region 1 is the 50% power level, and then nominal control rod. And then we have labeled as 1, 2, 3, 4, 5, 6, 7, 8, 9. And region 6 represents the nominal power region with 100% power output. We have 4 cases of simulations experimented here in this presentation. First, we will make local control, changing the power from 100% to 90%, and then back to 100%. And then secondly, we will apply this controller for global operation. The controller trained in the nominal operating point is used without further training for other operating region of a 50% power level changes. And then thirdly, it will be also used for emergency operation. The power is from 100% to 25%, which means we have a huge step down from region 5 to region 3. Finally, we will also simulate the shutdown and the startup operation by changing the power from 100% to 10% and then back up to 100% using a ramp function from region 5 to region 3. First, this is the local operation in the nominal region. Power is changed from 100% to 90% and then back up to 100%. And that power is shown in graph A. And the graph A, power was 100% and then changed to 90% and then back up to 100%. So you have some overshoot of the power which is acceptable. However, more important parameter or variable is B, which is temperature, because temperature is giving a thermal stress to the mechanical component. So we want to have a thermal, the temperature changing very smoothly and yet very rapidly. So this is the temperature or exit temperature response. And then finally, C is control rod speed. Control rod is moving with quite a bit of overshoot in order to produce the response that we are having. So this one, as you can see, we have a solid line and then dotted line. Solid line is the reference model which we want to follow from reference model. And then dotted line is the response using neurocontroller. As you can see, there is no distinction. So you have a perfect match of the reference model by using neurocontroller. Second case is now the same controller is used to control the reactor at different operating point of a 50% power level. So here we have changed from 40% to 50% and then again 40%. So the power is changed in graph A from 40% to 50% and then again 40%. And here the overshoot is acceptable. And in fact, that's what the reference model is producing. And the neural network is following exactly like that. And then the graph V is the temperature. The temperature is changing following this graph from 50%, 40% to 50%, and then 40% very smoothly without overshoot. And then C is control rod response. Here again, the dotted line indicates the planned response, and the solid line is for reference model, and you have a cross match of the neurocontroller. Third experiment is emergency operation. Now we are changing power, which is in graph A, from 100% down to 25% in a very short time period. And the temperature is also changing very smoothly following that without any overshoot. So this response is very much a desirable response in spite of the fact that neurocontrollers are trained in the nominal region, and yet on online control is readjusted for this kind of extreme operation. Finally, in case D, this is mimicking startup and the shutdown operation. The power is changed from 100% down to 10% and then backed up again to 100%. So we see that power is changing linearly, exactly the way we want. And also the temperature is changing linearly, exactly the way we want. So neural controller is capable of controlling on a wide range of the operating point without giving us any odd behavior. Graph C is the control rod response giving the power changes that we had, and the control rod is pretty much activated whenever you are making changes, and these are acceptable responses. So now, in conclusion, we talked about, first of all, how neural networks are used for controlling dynamic systems in general. And then we looked at numerous applications of control problems and identification problem in power systems. And then we looked at neural network architectures for modeling and control. Neural network paradigms also discussed in terms of a feed-forward neural network, and then radial basis function network, and then also a fully recurrent network. And then finally, we looked at diagonal recurrent neural network, DRNN, as a minimal realization of the architectures. And then we looked at how this DRNN is used for control purpose, and we applied that to nuclear reactor control. And we have seen that neural networks can be used effectively as a local controller, and yet it adapts its own gains in such a way that it can be applied over a wide range of operations. Thank you.
Dr. Lee's talk concludes our tutorial on artificial neural networks with applications to power systems. We would like to thank all our speakers for their contribution.
And would like to thank you for watching the tapes. We certainly hope that you have enjoyed the presentations. If you have any question or comment, please let us know. We encourage you to write to us. Our addresses are listed on page 4 in the tutorial book. Once again, I am Mohammed El-Sharkawi.
And I'm Dagmar Niebuhr. From all of us here on the program, have a good day.